Greetings all. The topic of this video is simple regression. First, we need to be clear that regression is based on correlation. Correlation provides a numeric index of the level of association between two variables. In contrast, regression is a versatile technique that uses correlated variables to make predictions and provides further examination of their relationships. Second, regression can be simple linear regression or multiple linear regression. In both cases, there is one dependent variable that is measured on an interval or ratio scale. Simple regression is the focus of this video, in which there is only one independent variable. This independent variable is also a quantitative variable, and it has a linear relationship with the dependent variable. If there is more than one independent variable, we need to run multiple linear regression. Multiple regression is not within the scope of this course and will be discussed in more advanced statistical classes. Regression is frequently used to make predictions. Prediction is the process of estimating scores of one variable y on the basis of knowledge of scores on another variable x. The regression analysis begins with selecting dependent and independent variables. Since simple regression is an extension of Pearson's correlation, both variables need to be quantitative and share a linear relationship. The independent variable x is also called the predictor variable. The dependent variable y is also called the predicted outcome or criterion variable. If you recall, the correlation between x and y is the same as between y and x. However, in regression, the relationship is directional. The information of x is used to make predictions of y. If you are uncertain about the variable selection, you can approach it from a conceptual perspective by designating the variable from which predictions are made as x, the independent variable, and the variable that is being predicted as y, the dependent variable. For example, it is reasonable to use age to predict income, not the other way around. From a statistical perspective, the variable for which information is easily gathered should be treated as the independent variable, and the variable for which information is hard to obtain should be treated as the dependent variable. For example, in smoking habit and the probability of lung cancer, the former should be independent and the latter dependent. In simple linear regression, the predictions are made not only based on linear correlation, but also the concept of the linear equation. If you remember from high school algebra, a linear equation is in the form of y equals b times x plus a. A linear equation is needed because simple regression uses a straight line to summarize the relationship of x and y. And the regression line is mathematically expressed as a regression equation, y hat equals a plus bx, where y hat represents the predicted y values. For every x value, there is a predicted y value. The equation can also be written as y equals a plus bx plus e, where e represents residuals. Because the accuracy of the prediction can only be as good as the correlation allows, with stronger correlation leading to more accurate prediction. Unless the correlation coefficient is either -1 or +1, there are likely differences between the observed y values and the predicted y values. The difference is called residual or prediction error. E equals observed y minus predicted y. Now, there is a question. When we look at the scatter plot of the two variables, many straight lines can be drawn to show the general trend of the data points. How do we choose a regression line that makes the best prediction of y? In making predictions, our goal is to minimize the differences between the observed and the predicted y values. This goal is met by finding the line of best fit using the method of ordinary least squares, OLS. Since the prediction error is the difference between the observed and the predicted y values, the OLS method aims to find the values of A and B in the regression equation so that the prediction errors are minimized. Since the prediction errors can be positive or negative, mathematically, what is being minimized is the sum of all squared residuals. Once we have the estimated values for A and B, the line of best fit is identified among all possible candidates. In other words, to write the simple regression equation, there are two parameters to be estimated, A and B. A is called the regression constant, which you may know previously as the y-intercept, and B is called the regression coefficient, which you first encountered as the slope in linear algebra. Skipping the mathematical details, I'm happy to give you the formulas to calculate the values of A and B. Based on the OLS estimate, the formula for calculating the regression coefficient B is the sum of the cross products of the deviation scores of x and y over the sum of squares of x. Once B is known, the regression constant A is the mean of y minus B times the mean of x. Please be reminded that the regression equation for predicting x from y is not the same as the regression equation for predicting y from x. Let me illustrate simple regression using an example. In this data set, I have the scores of 8 students. I would like to use their scores on test 1 as the independent variable and see if the scores on test 1 can predict their scores on test 2. That is, the test 2 scores are considered the dependent variable. Once it's confirmed that the two variables have a linear relationship, we need to estimate an equation in the format the predicted score on test 2 equals A plus B times scores on test 1. After going through the calculation, you can see that the value of B, the regression coefficient, is 0.862, and the value of A, the intercept, is 11.17. Therefore, the regression equation is the predicted y value equals 11.17 plus 0.862 times x. With the regression equation, it's easy to make a prediction. All you need to do is to substitute the x value of the case being predicted into the equation and solve it for the corresponding predicted y value. Based on the example of the test scores, if a student got 70 on test 1, her predicted score on test 2 would be y hat equals 11.17 plus 0.862 times 70, which gives a predicted score of 71.51. In other words, a student who got 70 on test 1 is predicted to score 71.5 on test 2, plus or minus the error in prediction. One thing to be clear about is that for a given x value, there is only one predicted y value, which is the value on the regression line for the corresponding x. This means that the regression line is a collection of all predicted y values. If you need to draw a regression line given the regression equation, it's pretty straightforward. You need 2 points to draw a straight line. If there's no additional information, all you need to do is randomly pick 2 x values, plug each of them into the regression equation, and get the corresponding predicted y values. Now, use the first x value and its predicted y value to plot the first point on the ordinate. Then repeat the same process with the second x value and its predicted y value. Once you have the 2 points, draw a straight line to connect them. That line is your regression line. It helps to know that the regression line always passes through 2 special points. The first special point is when x equals 0. Y equals the regression constant. The second special point is the mean of x and the mean of y. Knowing these 2 special points can save you some calculations when drawing a regression line. Conceptually, the regression line represents the average change in the dependent variable y that is associated with a unit change in the independent variable x. Specifically, the slope of the regression line is defined as the amount of change in y that corresponds to a 1 unit increase in x. In the test score example, b equals 0.862 means that for every point of increase in test 1 scores, there is a corresponding predicted increase of 0.862 in test 2 score. The sign of the slope indicates a positive or negative relation, but unlike the correlation, the value is not limited to -1 to +1. A slope equal to 0 would indicate that the line is parallel to the x-axis. That is, there is no relationship between x and y. The regression constant is simply the predicted y value when x is 0. We previously demonstrated how to test the correlation coefficient rho equals 0. In regression, we also test the significance of the regression coefficient. The test information is provided in the SPSS output. We follow the same 5 steps to interpret the values and report the results from the SPSS output. The test starts with the null hypothesis, which states that the regression coefficient is not significantly different from 0, meaning that the independent variable does not significantly contribute to predicting y. The alternative hypothesis states that the regression coefficient is significantly different from 0. Assume that you chose an alpha value of 0.05. You can find the observed t-value and its associated p-value in the SPSS table titled Coefficients. The t-value is calculated as the estimated sample regression coefficient minus hypothesized coefficient value over the standard error. The hypothesized value is 0 by default. You do not need to do any hand calculations. Simply compare the p-value with your alpha value to decide whether to reject or fail to reject the null hypothesis. Actually, the test for the regression coefficient in simple regression, beta equals 0, is just another version of the correlation test, rho equals 0. The two tests yield identical outcomes. This is because the regression coefficient B is related to R. Mathematically, the regression coefficient B, when predicting Y based on X, equals the correlation between X and Y times the ratio between the standard deviation of Y and the standard deviation of X. The relationship between B and R takes us back to the starting point. Regression is based on correlation. That being said, the regression equation allows us to think about the relationship between the two variables of interest in a more intuitive way, using the original scales of the measurement rather than standardized scores. Another difference is that regression analysis yields a formula for calculating the predicted value of the dependent variable for specific values of the predictor variable, even though the regression equation does not always accurately predict the actual Y values. Next, I would like to discuss the underlying assumptions of linear regression. It's important to conceptually understand the 4 underlying assumptions in this class. First is normality. The interpretation of normality varies depending on the textbook. In most introductory statistics courses, normality refers to the normal distribution of the dependent and independent variables. It's actually more about the normal distribution of the residuals. The best way to verify this assumption is to create a distribution of residuals with a normal curve overlaid to visually examine normality. Second is independence. All subjects in the regression study must be selected independently of each other. This is not something we can verify statistically. Researchers must ensure independence during sample selection. Third is linearity. It's the requirement that there is a linear relationship between the independent and dependent variables. Simply use a scatter plot. Fourth is homoscedasticity. This assumption requires that the distribution of prediction errors is about the same in both size and direction at all levels of X. More information will be provided about how to verify it when you learn multiple regression. What we have been talking about is unstandardized regression. Not surprisingly, there is a version called standardized regression. If the variables X and Y are standardized before running regression as described above, the results are standardized regression. Both standardized regression variables have a mean of 0 and a standard deviation of 1. So the regression coefficient beta will always equal the correlation coefficient R. The regression constant is always 0. The standardized regression equation is predicted value of the standardized Y equals R times the standardized X. The standardized regression offers another perspective for interpreting R. The coefficient tells the number of standard deviations that the dependent variable is predicted to change, given a 1 standard deviation change in the independent variable, everything else being equal. The last part of the video covers a few miscellaneous topics. First, we touched on the concept of coefficient of determination, R squared, in the discussion of correlation. It's a concept more appropriate for regression because it indicates how much of the variance in the scores of y can be explained or attributed to the variance of x. Second, we know correlation is not causality. Regression is based on correlation. Even if you can make accurate predictions, regression does not imply a causal relationship. Third, a sufficient sample size is an important consideration. In regression, the requirement is at least 20 subjects for each independent variable. Finally, do not extend the interpretation of regression outside the range of the original data set. For example, if you used a sample of people from age 30 to 60 to predict income, the regression model should not be used to predict income for those who are younger than 30 or older than 60. I have a separate video tutorial to show you how to run simple linear regression in SPSS. Here is a summary of the regression analysis based on the test score example. First, use a scatter plot to verify the linear relationship between x and y. Then, run the regression in SPSS by going to Analyze, Regression, and Linear. Based on the output, the coefficient of determination R squared is 0.882, meaning that about 88.2% of the variance in test 2 scores can be attributed to the variation in test 1 scores. Based on the ANOVA table, this is statistically significant at p less than 0.001 level. With a statistically significant regression model, we then check the test of significance for the independent variable beta equals 0. In the coefficient table, we see t equals 6.707 with a p lower than 0.001. And the regression constant is 11.17. So the unstandardized regression equation is y hat equals 11.17 plus 0.82 times x. And the standardized equation is the predicted zy equals 0.094 times zx. The standardized regression coefficient 0.94 means that for one standard deviation increase in test 1 scores, the predicted increase in test 2 scores is about 0.94 standard deviation, which is quite strong. You also need to check the assumptions of normality and homostaticity before drawing a final conclusion. I hope this video helps your understanding of simple regression. Thank you for watching.